let's take a look and understand photon-electron spectroscopy, which gives us evidence for the valence shell orbital model, or electron configurations. So first, some fine print. You do not need to be able to explain anything on this slide with the exception of the graph. But so if you'd like to fast forward ahead, that's certainly okay. Let's take a look at what actually happens. X-rays, which of course are very high energy, will be blasted at atoms. Here they are down here in the sample. And electrons are held in orbitals with different amounts of energy. The binding energy holding electrons in place will vary from 1s2 to 2s2 and out to p orbitals and so on. So what happens is that the electrons are blasted off, and some electrons will be moving faster as a result, and those fast electrons will end up at one place on the spectra, and then other slower electrons, as they're blasted off, some electrons may move slower, and those electrons will end up in other places on this graph. And ultimately, it will be able to tell us about how tightly, or what is the binding energy for each of the electrons in the different orbitals. Here's a PES, photon-electron spectra, for aluminum. Now AP won't often tell you that it's for aluminum. They may, or they may ask you what element is this for. But first thing we want to notice is that the numbers on the x-axis go from larger to smaller. Notice 1,000 energy, often measured in mega electron volts, and proceeding along the axis down to a lower value. This is by design so that the left side, in fact, can represent the nucleus. It's not meant necessarily to be that way, but you can think of this as the nucleus, and that will help you apply an electron configuration to all of the peaks in the spectra. Each peak will represent a separate sublevel. What type of orbital? An s orbital, a p orbital, and so on. And the height of the peak will indicate the number of electrons. So the first peak that you see on any spectra, this one written here, will always represent the 1s electrons. And unless it was a hydrogen, in which the peak would be smaller, of course, only this tall, then the first peak will represent a 1s2, as is the case here. The second peak, which is the same height, will represent 2s2, and the third peak, notice, is 3 times as tall, and thus it will represent a 2p6. The next peak along, less energy, again remember the energy is going down as we progress across, will be the 3s2, since it's the same height, and then we end with this lower peak, which must be representing half the number of electrons, or 3p1, which allows us to realize that this is the photoelectron spectra for aluminum. Here we have a graph with 2 separate spectra, one in black and one in red, overlaid on the same graph. This question asks you to determine which element is represented by the black peaks shown below. You probably answered oxygen, and you would be absolutely correct. And you can apply that the first peak is 1s2, the second peak of the same height would be 2s2, and because the third black peak is twice the height, we end up with 2p4, which corresponds to oxygen. And the red peaks would represent which element? And if you answered carbon, you would be correct, because you can see that the last peak is only half the height, allowing you to realize 2p2, which corresponds to oxygen. Now that's pretty straightforward. AP is more likely to ask you a why question. So if we look down below, we would need to explain why the black peaks of oxygen are to the left and not in the same exact location. Somebody might think, well, wouldn't a 1s2 for any element be in the same place on the graph? Explain why, in fact, the oxygens are higher energy compared to the carbon, or their binding energy. Why is it that the 1s2 electrons of oxygen are held more tightly than the 1s2 of carbon atom? And so the important, of course, issue would be the number of protons in oxygen compared to carbon. Because oxygen has an increased nuclear charge, that means that the oxygen electrons will be held more tightly, a higher binding energy, and that means that it's more difficult to remove, putting oxygen to the left, which would correspond to more energy required.